I'll see what I can do about that. So hello, everyone. My name is Lukáš. I'm a principal software engineer at Red Hat. I have been with the OptaPlanner project for, I think it's been at least a decade now. And I am the primary developer on the Constraint Streams API. So therefore the topic of the evening tonight. We actually introduced Constraint Streams, I think it was a little bit over a year ago. And this is the first public talk I'm doing on the topic. So fingers crossed it goes well. So I did already introduce myself. Let me introduce a little bit the talk. What are we going to be doing today? So I'm going to be talking about some of the basic concepts of Constraint Streams. I'm going to be describing how to get some of the basic things done, and then I'm going to get into maybe some of the more advanced considerations. But I want to say one thing first. This talk does actually require some prior knowledge of OptaPlanner. Specifically, I'm going to assume that people are familiar with what a scoring function is, what a planning entity is, planning variable, planning solution, those kinds of things. If you're not familiar with that, I recommend that maybe you watch some of the other talks in the OptaPlanner week first, and then you can come back to this talk in the recording, and everything's going to be just fine. I am going to be doing some pauses. I think there's room for 2 or 3 pauses for questions. So Karina, feel free to interrupt me then. And with that, I'm going to get started. So why are we doing constraint streams? Why is DRL not enough? Why is incremental score calculation not enough? Why are we doing constraint streams? I'm going to start with DRL. So we have found out over the past years and months and what have you, that Java developers don't really want to learn this whole new syntax of DRL and don't really want to learn this whole new way of thinking about your data in your memory and how you want to go through them. So DRL obviously does bring that, and that's a little bit of a problem for us. The second problem is that the IDE support is, pardon the pun, not ideal for DRL. So for Java developers and for people who are new into this sort of thing, DRL, we think, is not the best thing where you could start. So why not, for example, the easy Java calculator? That's really easy to write for Java developers, and it's really quick to write a easy score calculator for your problem. Unfortunately, just as it's easy, it's also very slow. It's the slowest option you can get for most problems. And it doesn't support score explanations. So easy is good for proof of concept, not so much for production, I would say. What is really awesome for speed, and I mean actually raw speed, is the incremental Java score calculator. The speeds you can achieve, scoring speeds you can achieve with the incremental Java scoring calculator are really, truly awesome. Unfortunately, it's outweighed, in my opinion, by how hard the incremental Java score calculator is to write. And Duncan's already talked about that in his talk yesterday, so I'm not going to go into that too much. Just please take my word for it, take Duncan's word for it. Incremental Java score calculators are hard. So constraint streams are actually our idea of the middle ground. They are written in plain Java, so the learning curve is okay. Their performance is on par with DRL, because under the hood, they do actually use drills. They are capable of explaining the score, which once again is important for production. And we also have some unit testing tools available for testing your constraint streams, which I hope to be able to get to at the end of my talk. So without further ado, let's jump into the anatomy of constraint streams. And let's start with a constraint provider. So what you need to do to tell OptaPlanner about your constraint streams is you need to implement the constraint provider interface. You see that right here. That's an interface that's in the public stable OptaPlanner API. And if you implement an interface, you are going to be required to give us this method called define constraints. which accepts a constraint factory as an argument. That's what we give you. And it returns an array of constraints, which is what we expect you to give us. As you can see, the array of constraints is assembled in this example simply by calling various methods. Each of these methods does return one constraint, and those methods are what's actually implemented. These methods are how the constraint stream is actually implemented. So let's move on to that. This is how a simplest possible constraint actually looks like. So it's a method. The reason for why it's a separate method will become obvious later. The method does accept the constraint factory I already spoke about, and it does return a constraint, which, once again, I already spoke about. So the important thing here is that everything in the body of this method, all of this here, from the return to the penalized, all of this here, that's the constraint stream. So what is a constraint stream? How do you create a constraint stream? You take, sorry for that, you take the constraint factory and you call a method from with some class as an argument. Now, this class tells the constraint stream to load essentially all of the facts or entities of the type cloud computer from your planning solution and to send them downstream throughout the whole constraint stream, one after another. So in this case, we are selecting from the planning solution all of the cloud computers, and we send them all the way down through the constraint stream. In this particular case, it's not a very long way because the constraint stream is immediately terminated by the penalize call. Penalize call terminates constraint streams. There can be nothing after the penalize call. And this actually makes sure that each of the cloud computers that reaches the penalize call will be penalized by a score of 1 soft multiplied by the cost of the computer. We will get to it in a little more time. So, bit more formally, what does a from do? So from construct, it operates on planning entities and problem facts from the planning solution. And for the remainder of this talk, we will just call them facts, both of them together. And it does return a constraint stream of facts where the type matches the one that you requested in from. So in this case, it would be a constraint stream of cloud computers. One thing you need to understand is that the facts is that if the facts are planning entities, the from will only send down to the stream the planning entities that already have been initialized, that have already gone through the construction heuristic. This is actually a difference from what you would see in DRL, where in DRL you have to do a lot of null handling to make sure that the uninitialized entities are actually excluded from your calculations. In constraint streams, it is completely the opposite. We exclude the uninitialized ones by default, and if you want them included, you have to do something extra, which I may show you later. This has been designed with the idea of simplicity in mind. So we don't really want constraint streams to be this long strings where you're doing a lot of null checking, null handling. We don't want any of that. We want constraint streams to read really fluidly, really plainly. So this is one of the assumptions we are making. The second concept you've seen in the first constraint stream I've shown you is the penalize call. And there are essentially 3 parts to a penalize call. First is the constraint name, which is supposed to be unique across the entire constraint provider. But besides that, you can put literally anything in there, anything human readable. It's an identification of the constraint, mostly for the human. The second part of a penalty is a constraint weight. In our case, it was a soft score of 1. So the constraint weight is actually a constant. and it's describing how heavily the penalty should be weighted. The third part of a penalty is a match weight, and that's a dynamic number. That's a dynamic number that is derived from what is coming through the constraint stream. So when the cloud computer is coming through the constraint stream, we are actually saying that the match weight is the cost of that computer that has come from the constraint stream. So the total penalty will be the constraint weight, which is the constant, multiplied by the match weight, which is the dynamic number that comes from the constraint stream. So assuming we have a computer with a cost of 2, then the impact in the score would actually be -2 soft. That's what this times this does for you. Now, obviously, in some cases, you may not want to penalize. You may want to reward some situations. And in that case, you simply swap out the penalize call for a reward call. Everything else stays the same. And the impact on the score will instead be positive. With that being said, if there are any questions, we can probably pause now. Karina, I'm not watching the YouTube channel, so you will have to tell me.
I will tell you, Lukáš. There are no questions so far. If you have questions at home, feel free to send them over, and I'll bring them on the next pause.
Okay. So let's move on into controlling what actually goes through your constraint stream. First, a useful thing you can do with a stream is you could filter it. This does actually the very same thing that a filter in Java 8 streams does, and this whole API is heavily inspired by the Java 8 streams. So a filter essentially takes everything that is coming from the beginning, and it applies a filter to it. So, for example, if you take the computer here and you check its cost, and the cost is greater than 5, that means that this particular computer will go on into the penalize call, but no other computer where the cost is smaller than or equal to 5 will move on into penalize. So essentially, this is how you control in a very basic manner what gets penalized and what doesn't get penalized. One interesting thing here is that you can see that I have actually chosen not to include the match weight. And if I choose not to do that, then the match weight by default is 1. So the impact of this particular penalty will be -1 soft, because we are requiring 1 soft and it's a penalty. So it's going to be a minus. Now, this what you've just seen has been...
I know you have pauses, but could you please go on back to the previous slide?
Sure.
We don't miss the timing. So what would happen if the computer.getCost returns a negative number? Is a question for Doormat.
So if it returns a negative number, that's very simple. I mean, the filter just accepts a regular Java Boolean condition. So a -1 is not greater than 5, so the result is false. That means that the filter is false, and that means that the cloud computer will not pass to the penalize call. This is really nothing but a Java condition. In this case, it's represented as a lambda.
Mm-hmm. Good. And will you show any example of how to bring 2 entities into the constraint streams?
Yes, give me a couple slides.
Okay, thank you.
Okay, moving on. So this was a very simple example of how to filter a stream. And that was without any sort of context. You could only use what's already coming to you from the from call. So let's take a look right now at how you can filter the stream using context, using some other stuff you have in your planning solution. So this we already know about. This is our standard from. And the new thing here is this if exists clause. And what we're saying here is that we only want this cloud computer to be penalized if there exists a cloud process on the planning solution where the computer is equal to the result of the method getComputer of that process. So essentially, when there is a process assigned to a computer, that's when we want to penalize the computer. I'm going to go into details on this on the following slides. So just try to remember this particular construct. We have a from, we have an if exists, and we have something which is called the joiner right here. And I'm going to explain joiners on the next slide. So what does if exists do? So if exists will only propagate a fact from the constraint stream downstream if some other fact is available. And by available, I mean it's available in your planning solution. So it could be either a planning entity or a problem fact. Now the condition is met even when just a single fact of that type, of this type, exists. But you need to understand that the fact itself cannot be accessed further downstream, right? So even after this condition is met, you still only have a stream of cloud computers. Not you cannot use the cloud process after the if exists is done. If you want the opposite effect, if you want to check if something does not exist and then you want to penalize it, then we also have the if not exists, which behaves exactly in the opposite manner to if exists. But I've actually mentioned something which was called a joiner, and that actually requires an explanation because that's a very important concept that we will get to see in the later slides as well. So a joiner essentially specifies effects intended relation to another fact. So for example, if we said, so if we're using an equal joiner between a class of between an instance of type A and an instance of type B, it's saying that we want the joiner to match when the value is Java equals to the other value. So in our example, and I'm going to go back to the example just to be sure, in our example, we are saying that the computer, this one, that the computer has to be equal to a computer that's coming from a process. So if you take a look here, that's the blue thing. That's the part on the left. The computer, we are calling a function on the computer, and that function returns the same computer. So we will be comparing this computer against the computer returned by this particular call, by the red call. So we take the process coming from the if exists part, and we return its cloud computer, and we will then compare this computer to this computer. And only when these two computers actually equal, only then this whole thing will be true, and therefore we will be penalizing the cloud computer. That's what a joiner does. It specifies a relationship that we need to be true for something else to happen. In this particular case, we are saying that the two computers need to be equal. In other words, there needs to be a process running on that computer for the computer to be penalized later. We do have some joiners that are available out of the box. You've already seen the equal joiner, but we also have the greater than joiner, less than joiner, greater than or equal, less than or equal, etc., etc., for objects implementing the Java compatible interface. And we also have the joiner called filtering for when the other joiners are not sufficient. So essentially, once again, you can put any lambda in here that returns true or false, and then that will determine whether or not the if exists or if not exists actually will match. Now, the reason why I'm mentioning the filtering joiner is for completeness, but I'm actually going to tell you to avoid it if you can. Because all the other joiners, the equal, the greater than, on all of them, they actually allow for better performance through indexing. Unfortunately, the filtering just accepts a lambda, just accepts a predicate. So we don't know what the operation inside is, and therefore we cannot properly index the call. So even though it will do what you want it to, this filtering joiner, it will not do it as fast as whatever you are able to do with the equal joiner, greater than joiner, etc. The same actually applies to the standalone filter call I have shown you earlier. So once again, if you're able to do something with a joiner, do it with a joiner and avoid filtering. There is nothing wrong with filtering. Sometimes you have to use filtering, but joiners are just going to be faster. For a complete list of all the joiners, feel free to look at this class in the public API, and that's going to give you all the info you need. And yeah, I think that this is another good place for a pause.
Oops, I'm sorry, I was on mute. Yeah, please go on. We are fine so far. People are loving the talk. Thank you.
Good. I'm glad to hear that. So one more thing, and that's actually answer to the question from before, how you put two things inside a stream. This is how you put two things inside a stream. We call this a join call. It's a little similar to what you may be familiar with from SQL. And it essentially does a couple of interesting things to the stream, and I'm going to describe them all now. So we have the same old from here, from Cloud Computer, nothing fancy there. But now you should know this, that it actually returns a unique constraint stream of Cloud Computer. So it's a constraint stream that only contains that only makes available one thing. Now, after you call the join, you will actually see that it returns a by constraint stream of a Cloud Computer and the Cloud process. So we actually call it the cardinality change. The cardinality of the stream has increased from 1 to 2, from a unique constraint stream to a by constraint stream. Where before you only had a Cloud Computer in the stream, you now have a pair of Cloud Computer and Cloud process because we are joining with Cloud process. Then we have the usual penalize. But the new thing here is that because we now have a by constraint stream, we need to take two variables into account at once. So instead of just applying things on the computer, we need to apply things on both the computer and the process. In this case, we are applying them we are taking just the value of the process, and we are taking the required memory. So essentially, this penalty, the score impact of it will be proportional to how much memory the process requires. So we take all the Cloud Computers, we check for the processes that have that are running on the computer. That's the joiner we've already seen. It's the very same joiner. And then we penalize all the computers that have a process running on them by the number of required memory that by each process. So this is how you expand the stream from a unique constraint stream to a by constraint stream. Here you can see there's the join right there, and there's the change to a by constraint stream of a Cloud Computer and the Cloud process. And this, as I already mentioned, is now the by function from computer and process to some match weight. So what have we just done there? We have increased the cardinality of a stream. And we've done that via a join. Join makes the matched facts actually available downstream. So that's what you've seen. You now get the by constraint stream of the computer and the process, and you can access both in the downstream blocks. One very important thing to understand about a join is that a join creates a Cartesian product of what's in from and what's coming in from the join. So if you assume that you have two facts coming from, and you have three facts coming from B, the end result will be 6 unique pairs of all the A's and all the B's. So you need to understand that whenever you join, you're possibly evaluating a lot of things, which could affect your performance. So that is where the joiners actually once again come in. You only wanna create a product of the things that you're interested in. So in your joiners, make sure you're always as specific as possible. make the product as small as you can, because only if those products are small and only if those products are only containing things you're interested in, only that way are you going to get the maximum performance out of the constraint streams. If you keep iterating over things you don't need, you're wasting time. So a little bit more formally on the stream cardinality. So if you do just the plain from, as we've seen in the first constraint stream, you get a result of unique constraint stream of the type you mentioned. You get one element in each tuple in the stream, and you have to apply a function from A to something or a predicate of A in your match waiters, in your filters, etc. If you apply a join on that, you get a by constraint streams of A and of B, which means you are going to have a pair of things in the constraint stream, and it means you're going to have to apply in your match weights and in your filters a by function of A and B to something, or a by predicate of A and B. So what happens if you join on a join? Well, then it becomes a try constraint stream, and you have to apply a try function and a try predicate. And if you do one more join, then it becomes a quad constraint stream, and you have to use a quad function and a quad predicate. And you cannot actually do any more joins because we only support everything up to quad constraint streams. One thing you should also understand is that you should prefer if exists to join unless you actually need downstream access to the matched fact. And that's because the if exists call, it will not actually create the Cartesian product. The if exists is true or false when just one element is found that matches the condition. So it is, once again, better for performance. If you don't need access to the joint fact, don't use a join. That would be my recommendation. And once again, if you have to use a join, be as specific with your joiner as you can, because performance is important. And I just want to be absolutely clear here. There is nothing wrong with using a join. Many, many examples use a join, and very often it's necessary to use a join. I'm just mentioning the if exists construct again, because sometimes it's not necessary to use a join. Sometimes you don't need access to the other fact. And in that case, if exists is most likely going to be faster. Another place for questions, if there are any.
Yeah, so again, I don't know if we are going to cover this difference later on the talk, but using DRL is faster or constraint streams? This is the question of the day. Do you want to talk about this at the end?
I do actually have a slide for that at the end, so I'm going to keep it there, okay?
Perfect, thank you.
Yeah. Any other questions?
We are good to go.
All right. So this is what we've done so far. We have taken a look at simple penalties and rewards. We have learned how to filter the stream with a filter call and the if exists call. And we have learned how to increase stream cardinality with a join call. And what comes now actually is like something like the pièce de résistance of the entire Constraint Streams API. And it gets a bit hard to explain, so please stay with me. And this is the group by call. It's the crown jewel of the Constraint Stream API. It's the only way how to transform the stream and figure out some new knowledge from what you didn't know before. So if we take a look at the existing constraint here, the existing constraint stream here, we are actually doing from a cloud process now, and we are grouping those processes by the computer they run on. And for the group of processes that run on the same computer, we actually call a sum of the required memory by that computer. So think about that. We are going to separate all of the processes into groups based by the computer that they run on, and we are going to calculate a sum of the required memory of all of those processes on that one computer. The end result is going to be a by constraint stream of a computer and the integer, which is the sum of the required memory. So if you compare that with where we started with a unique constraint stream of a cloud process. And here we have the bi-constraint stream where the cloud process is no longer available. We have created something completely new, something completely different, and the cloud process is gone now. You will not be able to get to it through the constraint stream itself, because the current constraint stream is really only interested in the computer and the sum of required memories that the processes running on that computer actually take. The next thing in that same stream is we actually filter all of those computers where the required memory by those processes is greater than the available memory, which means that at this point of the stream, when it enters the penalize call, we only have the computers where we have less memory than its processes actually use. So that computer is impossible. That is an overused computer and it cannot exist. So we actually add a hard penalty for that. And we make the penalty so big that it's actually the difference between the required memory and the available memory. So the worse that this computer is overloaded, the worse the hard constraint break is actually going to be. Because I understand that this is not perhaps the easiest concept to understand, I'm going to go into a bit more detail on some of the parts of what you are seeing here. So first, the power of group by, and I've already said that, is that it's the only element in constraint streams that actually allows you to create information that was not available before. You don't have this information in the planning solution. You most likely don't have it anywhere in your variables or in your entities. This is new information you didn't have before. And there is no other way how to do that in constraint streams than through group by. So understanding this concept is pretty important. And group by actually takes all the upstream tuples, everything that was there before, and creates a new transformed stream, which is most likely going to have a different number of tuples coming through it. It's going to have different tuples coming through it, and it's going to most likely have also a different cardinality. It's really most likely going to be an entirely different constraint stream at the end of the group by. How does that happen? So let's first talk about a constraint collector. That was the sum you've seen earlier. A constraint collector takes a group of tuples. So for example, a group of processes, and it returns a single result out of all of those. So in our case, with the sum, we took all of the processes and we created a sum of the memory required by all of those processes. We also have a constraint collector like count, for example, which would, for example, count the computers that the processes run on. Just an example. You can probably think about many, many other things you could do with the data model yourself. If you take a look at the constraint collectors class in the OptaPlanner stable public API, you will be able to find many, many other kinds of collectors like count distinct and some duration-based collectors, etc. So there is plenty to go with. But these two, I would say, you are probably going to be using most often. Another concept you need to understand.
Luca,
Yes.
Is group by similar to the accumulate in DRL?
It's implemented with an accumulate in the DRL, but it's much more than that. It's actually a whole small framework built on top of accumulate.
Okay, thank you.
So back to the original topic. The other thing you need to understand is what a group key mapping is. So a group key mapping, it turns a set of facts into a new set of unique facts. So it's a mapping function from A to B. So if you assume a stream of processes that we have seen before, and you choose a group key mapping function from the process to the computer it's running on, then the end result of applying a group key mapper would be a set of computers that the processes are running on. So for example, for the input, you see here, for a process 1 at computer 1, for process 2 at computer 2, and process 3 and computer 1, this would give the output of computer 1 and computer 2. As you can see, a computer 1 is only present once, even though in the input it's available twice, because the output is always a set. It's always unique, what you get as a result of the group key mapping. Because the computer 1 and the computer 2, they are the new groups. So let's take a more complicated example than that. Let's try a group key by mapping. So let's apply 2 mapping functions to the same data. So first is the same function we've seen before that returns a computer from a process, and then a second mapping function that returns a required memory from the process. So what happens if you map by both? If you map by both, you actually get a computer 1 with required memory 1. That's the first pair you get. That's here once. That's fine. You get computer 2 and required memory 4 as the second pair right here, because once again, it's there only once, this particular combination of facts. And the third pair you get, computer 1 and computer 3, that's what you only get once as well, because that's what mapping functions do. But this time, it's a result of sort of collapsing 2 different processes, because they have the same computer and the same amount of required memory. So they end up in the result, once again, as 1 pair instead of 2. That's what the group key mapping does. It always returns a set of unique items. So when we put all of this together, and this is like the final magic of group by, is you take the group key mapping function. So you take all of the computers from all of the processes, and you create a new constraint stream. You create a new constraint stream where the new keys are going to be the computers. And then for all the processes that share the same computer, you calculate a sum of the required memory for all the processes in the same computer. And obviously, as a result, you get the by-constraint stream of cloud computer and integer, and everything after that has to deal with this by stream and no longer with anything to do with the cloud process. So I know this may have been a bit hard to handle, so I'm expecting some questions here. Karina?
For now, we can move on because we have a small delay in between the streaming and YouTube. So if questions come around, I'll make sure to interrupt you and get back to it.
All right.
Okay, thank you.
I mean, if you guys don't have any questions here, then either you're awesome, which probably you are, or I suck at explaining. But anyway, moving on.
The explanation is great. Please go on.
The last thing, or actually the second to last thing I want to talk today about is how you test the constraints. So for that, we have something which we call the constraint verifier. You can apply that in any testing framework you like, so be it JUnit, TestNG, anything you can think of. And it's called a constraint verifier. Once again, it's a part of the public API, so it's something you can rely on. And it is how you test that your constraints actually return what they are supposed to return. First, you need to create an instance of the constraint verifier. It's very easy. You call the build method on the class. You give it your constraint provider. That's the very first thing you've seen in this talk. That's the very first class. You tell it what your planning solution class is and what your planning entity class is. That's what you need to do. And then you have a constraint verifier that you can use in your test methods. One of the test methods you can see here, This is just a plain test annotation from JUnit. As I already said, it could be anything else as well. And here is the important part right there. You take your constraint verifier and you say that you want to verify that some constraint, in our case, computer cost. So let me go all the way back. This method, so this method, that's a method reference directly to this method. That this method, when given these facts, which we have created right here, will penalize by 2. It's as easy as that. You give it some fact, and it will, and you make sure it will penalize by 2. If it doesn't, you will get a very clean, very nice exception where it tells you what's wrong, maybe even how you could fix it. And essentially, that's it. That's how you test constraints. 3 lines of code, actually, 4. This is just boilerplate to create the data set. One important thing to understand is that the constraint weights, soft, hard, anything like that, they are not actually tested here because we treat them as fully configurable. So since it's a configuration, we don't test that. There is a way to test that, but for the interest of time, I'm not going to go into that right now. So we just test the match weight. So that's the last part. That's the lambda you have to provide as the final argument in the penalize or reward call. So that was the second to last topic. And the last topic is this, and that's where I'm going to answer the last question. So the Constraint Streams API, is it the one API to rule them all? And the answer is, it depends. We have all of these ways I already mentioned of how to define a scoring function. We have the rules way, the easy way, the incremental way, and constraint streams. And the truth is that each of those is good for different things. So for example, if you want to do something really, really quickly, you don't want to spend too much time thinking about it, you just want to do a proof of concept or something, use the easy calculator. There's essentially no learning curve. It's very easy to use. It's harder to test, and it really sucks in terms of performance. It's not good there at all. If, on the other hand, you want really, truly awesome performance, use the incremental Java calculator. But be prepared to suffer while you're writing it and while you're testing it. And believe me, suffer you will if you decide to write your own incremental score calculator. So as I already said, there are different scoring functions available for different use cases. And the reason why we like constraint streams and why we introduced constraint streams is that, as you can see in this column for constraint streams, there is no red here. The learning curve is okay. As long as you're a Java developer, you'll be able to learn it. Performance is okay. It's actually nearly identical to DRL because constraint streams under the hood are the rules. So it has to have the same performance. It is the same thing. You just don't get to see it. And of course, the ease of use, hopefully, as I've demonstrated, is good. And the ease of testing, once again, as I've hopefully demonstrated, is also good. So even though we don't have any plans for deprecating any of these, we will keep all 4 of these for the foreseeable future. We don't have any plans on deprecating. We are quickly gravitating towards constraint streams as the default. All of the new things we're doing, they're already including constraint streams. And most of the examples that are currently available upstream already have their constraint providers. And those who don't, stay tuned, they will pretty soon. So constraint streams, even though it's not the only option, and it's not for every use case, we think it's the best we can do as a default, and it's actually going to justify a vast majority of use cases. That is what we think, and we are going to show that in the examples repo and in the quick starts and in the OptaWebs and everywhere else. So how can you find out more? We have a pretty comprehensive documentation. We have examples on GitHub where you can take a look. You can ask a question on Stack Overflow. We are there pretty frequently. And obviously, as you already know, we hang out on Zulip. So that is one other place where you can catch us. And with that, I'm done. And I'm interested in your questions. Thank you very much.
Wow, what a great presentation on Constraint Streams. Thank you, Lukáš Petrovický.
Don't worry about it.
Yeah, whatever. So what is the difference between score verifier and constraint verifier classes?
Right. So the score verifier has actually been designed to deal with the Drew scoring function. So as far as I know, you can only use it with that. If you're using constraint streams, you're going to have to use the constraint verifier or come up with something else that works better for you. But as far as I know, the score verifier can exclusively be used for the Drew scoring function.
If I recall correctly, it can actually be used on all cases, on all scorings, but it's much more pain to use. So with the constraint verifier, they say that the proof of the pudding is in the eating, and so the constraint verifier, the new way that Lukáš built, it's just much more beautiful. What you basically do is say, I want a constraint verifier for this function which returns a constraint. The score verifier is and if you see the classes that use it, it's much more cumbersome, much more code, much more verbose. Much less people use it because it's too much work.
And for the constraint verifier, I'm pretty sure about that. You can only use that for constraint streams. It will not work. There is no way actually to integrate it with anything else. So if you use constraint verifiers, you're writing tests for constraint streams and for nothing else.
Yeah.
Nice.
And good to
so
see
we have someone here using it. So let me ask another question, if you allow me.
Just 1 second. I just want to say Matej is a former contributor on OptaPlanner. So he's good to see him around.
Hey, hi.
Thank you, Matej.
So I don't see the YouTube, so I don't know who's asking the question. So hi, Matej.
So is it possible for people to write their own constraint collectors?
Yes. The constraint collector itself is an interface. And if you take a look at the constraint collectors class, you will see that it's relatively easy to write your own. All the code is right there. So yes, it's an interface. Anyone can implement it. Go for it.
Nice. And what about writing constraint streams from Business Central? Is it possible? Do you recommend it?
Good question. There is no specific user interface for writing constraint streams into Business Central. It's Java code. So as long as you can write Java code there, you can write it there. But there is no specific tooling to help you do that.
Good. And do you plan to convert employee rostering application to CS, to constraint streams? I'll just call it CS because it's a long word.
Sure. Yeah. We actually also call it CS. Yes, in my opinion, and I'm sort of the authority on this, constraint streams is the one API to rule them all. So everything in the world will be converted to constraint streams if I have my way.
I fully agree. There's just one reason why I think we haven't done it yet. With employee rostering, it's the consecutive constraints in a row constraint is difficult. It's very difficult to do it in DRL, but we found a way to do it, and now people copy it all over the place, of course. And I'm sometimes sorry that we created it that way because it's not that performant. So we're looking for a better way to do it in constraint streams.
One thing to understand here is that the API is constantly evolving. And by that, I mean the API is completely stable. We will not break what is there already. We just don't do that. But we will be adding new parts to the API that will make some things easier when we find a use case that needs to be made easier. So yes, the API is going to evolve. And yes, some of the examples are going to need new parts of the API to be actually implemented.
Nice. I think I missed this one from Dormet. Do you have experience with runtime user definable constraints in CS?
I'm not sure what that means.
I presume it means that can we have, if they can define constraints at runtime, right? New constraints at runtime. And so my first answer to that always is, in most of the time, you can write your constraints very generically. So instead of saying, I want to have a constraint that says that certain people want to have Friday off, you write a constraint that you say, when there's a particular time that somebody wants to be free, then particular time range, and it could be a day, could be half a day, could be a week, then add in a data element for that and match upon that, right? But there is a real demand on, can we define constraints randomly? And we're doing some prototypes around that, right, Lucas? When we will deliver those, that's an interesting question. Yeah, we want.
So technically, if you want to reconfigure your solver, you can inject at runtime to the new solver anything you want. So if you have a way of generating Java code, for example, yeah, go for it. But it would have to be a new solver instance at the moment.
Yeah, and I think yesterday they were doing that, so Daniele and so forth, because they were talking about generating some of the constraints, I think maybe with Gizmo or something like that. If you want to do that, Gizmo is a really interesting piece of technology for that, or at least want to do it in the future.
Mm-hmm. Good. And what about, do we plan to reach DRL parity in functionality?
Yes and no. DRL is...
gosh! The default answer for every question in technology is, it depends. It's the default, right?
Exactly. I mean, it's really true. I mean, DRL is a generic language for data processing. We do not intend for constraint streams to be a generic language for data processing. So there are some things you will never be able to do with constraint streams. But we do, and I think I am able to make that promise, we do want to see every use case in OptaPlanner be implemented in constraint streams. So whatever it takes, we're going to look into it. But no, it's never going to be one-to-one with rules, ever.
Perfect. So we would like to get back to another question that we had before. So Lukáš, if you want to stop your screen sharing, and just go back here so you can look at it too. So what about that fairness distribution, guys? How can we show our guarantee to the person that we are not favoring this versus that person? Could you talk more about this?
You want me to take this one? So there's a good way of doing that, by the way. So what you can do is, so let's suppose you have you need to assign employees to shifts, right? And you have a number of employees who are asking a day off on Friday and on Christmas. Everybody wants to be free on Christmas Eve, right? So how do you decide who gets that Friday day off and who gets that Christmas day off and so forth? First of all, you add the fairness constraint, which basically says if you get whoever gets the most of their days off that declined, that penalty gets squared, get multiplied by itself, which basically means that OptaPlanner will try to first make sure that whoever's worst off is as best off as possible, right? And then it will try to look for the second person worst off and try to make that person best off as possible and so forth. That's how you organize your scoring function. This is important because it's very easy to make everybody happy. It's just put except for one person and just have that one person do all the work, right? And that that person will quit, and then everybody's unhappy again and your system won't work, right? So that's the first thing you do. But that won't guarantee you that by arbitrary, the same person always draws the short straw, right? So how do you force that not always the same person draws the short straw? Is that when you, well, in the planning window, it will actually guarantee you that not the same person always draws the short straw. Because if you have 2 or 3 rejections of your request of a free day, then that gets squared. So as soon as you have 10, you have 100 points there. So if 20 other persons all get 2 days of declined, then they only go up to 40. So your 100 outweighs that, and OptaPlanner will definitely start moving your declines to distribute across the others. However, what happens with historic declines? What happens with things that are not in the planning window? And there's 2 ways to deal with that. Either you load all that data in your planning problem as pinned entities, in which case OptaPlanner will calculate them wrong, and they will go through all of the constraint streams, and you might see some smoke coming out of there. Or at some point you say, okay, I'm just going to look back up to a month, and anything before that, I'm going to summarize that, and I'm basically going to keep a record. For example, how many Christmas did this person get, right? How many days off request did they decline, right? And once you do that, you can just add another constraint that says, that needs to be fair too, right? You can imagine that if you got Christmas off last year, and somebody else didn't, then the other way, it should be the other way around this year, right?
Perfect. Could it be more clear than this? I'm just kidding. Lukáš, do you want to add something to the fairness distribution?
Just one thing, perhaps. It's one thing we don't have in Constraint Streams yet. It's on my roadmap. It has to be there.
And we're going to make it. It's with Constraint Streams. We have syntactic sugar, right, Lucas? So we can probably make this something like penalize fairness. That's what I'm thinking.
Yeah, I like that.
We'll discuss that.
So somebody asked what's written here. So it's just redhat.com. We have all these swags that we own. We have to use it, right? We are like on the pandemic. We are at home. So let me use my swags. So for people who are watching, we are on the September 2nd of 2020. So Lukáš said that this is on his roadmap. Let's go back and see this a couple of years later or months. I don't know.
Sorry about that, Lucas.
Let me see here. We are almost at top of the hour, but let's grab a couple of more questions. So is it possible to collect a group by, for example, A has X, B has Y, C has X, groups to, It's better if you read it instead of me reading it.
Oof. Let me see. I don't have a very clear picture of how that would look right now. But if you just reach out to me on Zulip, we can think about that a bit more, and I'm sure we can come up with something.
One of our design principles was that what you could be able to do in an SQL group by, we would like to be able to do in a constraints group by too. So if you have any examples that won't fit in SQL one, we definitely want to be able to, that fit in an SQL one and don't fit in ours, we want to be able to do those. And of course, we do much more on that because you can pass in any Lambda function in there, right? Which you cannot do with SQL.
Nice. What about squaring the scores? Is it possible to use 64-bit integer numbers for scores in DRL? I've had overflow problems because of that.
So the good thing about, I'm not going to speak about DRL here. But the good thing about constraint streams is that you can actually, from the constraint collectors, you can actually have that return literally anything. So if you write a constraint collector that does your sums and counts into big decimals, big integers, go for it. Nothing's stopping you.
Yeah. And also the scores actually across all scoring function, easy, Java, DRL, and constraint streams, you can switch from hard soft score to hard soft long score, which basically gives you 64-bit integer numbers. And yes, overflow problems, we've seen them before. And what you actually get is then you get the worst possible, not the worst possible solution, but it overflows, and then a very, very bad solution becomes a very, very good solution according to people. It's a very simple switch. Just switch your score type. Add in long.
Thank you. So, Lukáš, thank you so much for the awesome presentation.